that letter, there were three main goals. The three main goals were to maintain global leadership in critical emerging technologies. So specifically, of all the science that was called out in that letter, the three were artificial intelligence. So Howard has an extremely strong presence in artificial intelligence. We also have a very strong, long history in quantum information, which is why we're here today. And the third is in nuclear technologies. It also was a call to revitalize America's scientific enterprise and to ensure that we have economic growth in the lives of Americans. The last thing that it did note was that President Trump started the National Quantum Initiative. So this was in 2018 in his last administration. And then there will be a secondary approach to this in this new administration to establish the foundation of national quantum supremacy, is the way that he puts it. If you look to the left, or I'm sorry, your right, one of the biggest challenges is to develop a quantum ready workforce. And there's specific challenges that we'll go through today. But truthfully, this is probably the largest challenge that we have, is to prepare students, faculty, researchers, and the infrastructure to participate in quantum. Now, quantum is a global game. There's about 42 billion US dollars invested around the world in quantum information. And it's what you'll see is that the US is not the leader in this space. We have around $5 billion to date focused on quantum, and our competitors have 3 times as much. And that's the reported number. It's probably much larger than that. So one of the things that we want to do is to make sure that all of our students and faculty are participating in what we like to call the quantum industry. And how can I say that it is a quantum industry? Well, it's actually publicly traded right now in many, many different states. So what you'll see over here are these end users. These are companies that you're used to seeing. All of them have quantum divisions. There's a quantum communications and computing division at JP Morgan Chase. They hire our students all the time. There's also a lot of the expected kind of fruits of when they actually build a quantum computer is in the space of quantum chemistry, our pharmaceuticals, our quantum for biology. So that's why you see things like AstraZeneca. If you move to the right, now you're actually seeing that there's different types of qubits. So the superconducting qubits have big names like IBM, Amazon, Google. You also have ion trap. We'll talk a little bit about ion Q in a second, but there's also these different modalities. So we're still in this space where not everyone is agreed upon on what exactly is the right qubit for our quantum future. However, all the companies that you see listed, small, big, otherwise, are hiring students and faculty and others to participate in quantum right now today. Now, one of the things that have also recently just happened this year is right down the road in College Park, the President Pines, which is there to second to your right, with Maryland's Governor Wes Moore, have what they call the Capital Quantum Initiative. So this is a $1 billion effort in the DMV, centered at University of Maryland College Park. University of Maryland's also doing a cluster hire that they just announced, all around this idea of building quantum around this ion trap or ion Q, which is publicly traded on the New York Stock Exchange. So this is right now today what's happening in quantum. Now, all that said is that I believe that HBCUs have an extremely important part to play in this. And with the IBM HBC Quantum Center, which we'll see a little bit later, this is the investment into HBCUs in this space. So IBM stepped up to the plate in 2020. And by virtue of investing in HBCUs, they also invested in the Southeastern United States. And it was not a lot of money, is what I'll say, especially for the job that's at hand. And why HBCUs? So if you haven't read this article, it came out in 2021. It says, "Where are the missing physicists?" It's in the Science magazine. And it talks about the role that HBCUs have played in developing physics, which is at the heart of quantum information science. So all of those dark colored, I'm colorblind, all those dark colored dots that you see are places, two places have graduated over a 20-year period, over 100 physics majors, Morehouse College and Xavier in New Orleans. And then as you go up the ladder, what you see is that the numbers get really, really, really small. However, you can see that the load has been carried by HBCUs. Another part that you can see is that these are for baccalaureate, so where students get their bachelor's degrees that are Black and African American that go on to get their PhDs. And I love showing this article because it shows just the impact of HBCUs, where you have places like University of Florida that have 35,000 students, or places like University of Maryland College Park that also has a large amount of students. That with respect to Black people getting PhDs, smaller places like Morehouse College and Hampton University still produce the same amount of PhDs in science disciplines as these other larger places. And then you have these two great outliers, right? One of which is Spelman College that has less than 2,000 students all the way at the top. And the other is where we sit right now today, which is Howard University. So this again shows the impact of HBCUs. And today is not the first time that a quantum scientist came to HBCUs to give a talk, right? At this point, Einstein was at the highest level that he could be. The other thing that people usually miss in this story was that Einstein was a member of the Black community in Princeton. So he knew how important it was to interact with Black people in this space. So he chose to go to Lincoln University. He got an honorary degree. He also did a public lecture. And literally every place in the world was trying to listen to what he had to say. But our story in quantum does not just stop with Einstein paying a visit to HBCUs. There were real quantum scientists that worked at HBCUs in this space, one of which was Elmer Imes. Elmer Imes was the second Black person to get his PhD in physics from the University of Michigan. This was in 1918. The first person to get their PhD was also in physics. So first Black person period to get a PhD was in physics from Yale. But with respect to Dr. Imes, he had a storied career at Fisk University. He was an expert in atomic spectroscopy, and he also advised the first Black woman to get her her graduate degree in physics from MIT, Carolyn Parker. She didn't get her PhD because she passed away because she was working in the Manhattan Project and passed away from complications from that aspect. At Howard, there's also another great physicist by the name of Warren Henry. So right there in Thurkield Hall, when you go up the hill and you see the physics building, this isn't in Thurkield Hall, but he did build cryostats in Thurkield Hall. And one of the things that I used to tell students all the time when I used to teach at our holiday resident in Walker is in chapter 42 on magnetism, they actually still show the data that he took while he was there at Howard University. He did, like many researchers at Howard, he worked at the Naval Research Laboratory. He actually started the physics department at Morehouse College, where I got my degree from. And he was a fellow of APS and also a SS. So he was a very accomplished scientist. And the last person that I will show is Herman Branson. So Herman Branson was actually the fifth Black person to get their PhD in physics, who from the EPR paradox, so this is Einstein, Podolsky, and Rosen. He got his PhD under the P, which is Podolsky, at University of Cincinnati. He had a storied career at Howard. He was here for 27 years. And then he actually performed research with Linus Pauling because his expertise was in X-ray crystallography. And while he was at Howard, he wrote this article to the American Journal of Physics, which the American Journal of Physics, I think it's actually coming out today. They are doing their International Year of Quantum Science and Technology special issue. I happen to be a guest editor on that. So shout out to Herman Branson again. But Herman Branson, he wrote this article called Physics Training for the Negro Student. And I didn't know this existed until I was a professor at Howard University when I came across this article and I read it. And I was like, this is exactly what I'm trying to do as far as preparing students for the quantum initiative in the same way that he was preparing Black students for the quantum event of the time, which was World War II and the Oppenheimer and the Manhattan Project. And one of the quotes that sticks to me, especially now today, being that the situation that we're in scientifically, politically, economically, is that it's not an issue of Negro colleges getting a fair share of the funding. It's actually the Negro College being an American institution that is training Americans to participate in an American issue. So quantum today is definitely an American national security issue. And I make the argument that not just Black physics majors need to be involved in this, but all Black people need to be involved in quantum. And taking that as inspiration, that's why we started the IBM HBCU Quantum Center. And it's meant to develop Black talent for the Black community across all professionals and academics. And also it's meant to expedite and foster quantum computing research and development. So this is just not a DEI program. It's not just curriculum. We are investing in research in this space as Black scientists. And today we'll actually have, as a part of our Women in Quantum series, we have Dr. Serena Eley, which I will introduce pretty soon. But we also have one of our Howard graduates, Victoria Abadeo, who is from Atlanta, Georgia. She was a physics major here. And she said that the best thing about being involved in the Quantum Center is that there's a community of HBCU students that are interested in quantum, that she gets to meet, and she gets to be a part of this. And she's now a second-year PhD student in the applied physics program at Harvard University. So this is one of our success stories. I'll show you many, many more, but this just shows you kind of the flavor of what we're doing. And we built this off of the Team Up report. So for those that aren't physicists, the AIP did a study on why there aren't a lot of Black physics graduates. And they attributed this to 5 factors: belonging, a physics identity, academic support, personal support, and leadership and structures. And we transformed these into our 3 pillars, which is to build this community, to foster a sense of belonging, to support our graduate and undergraduate students in research, and to connect our talent to quantum experts across the world. And we've been extremely successful at that. We have 27 institutions that, again, are across each of the Southeast. They are categorized by region, but also by research expertise. And then they also, each one of them have a PhD grounding institution and smaller institutions as a part of it to help to develop the pipeline. So for a student can go to UDC or Morgan State where they don't have a PhD in physics, and then they can matriculate to Howard University where we do have a PhD in physics, and ideally get a well-paid job with a great startup package at a new Research One institution like Howard University to continue their career in this space. And I'll talk about how important that is. But we have cohorts now of around 40 students, and we have 80 plus faculty that are engaged. We have a very high-powered research advisory board, which I'm a member of, and Serena is also a member of this, and all these great other Black scientists in the space. Donnell Walton is just now the assistant director of the UARC that's here on campus. So please, if you guys meet him, let him know all the great things that you're doing. These are kind of our activities. We do workshops for faculty. So there's a grant writing workshop that just happened in January. We also do training. There's access to the systems. We also partner with specific people. So Fermilab, Brookhaven National Lab, AMY is a consortium of HBCUs that have engineering programs. And then we also have our faculty award from SPIE. There's $100K each year competitive within our system. And just a little bit about Wes. So Wes is at Morehouse College. Wes got our first initial faculty seat award. Then he got the additional SPIE seat award. Then he got expanding QIS funds at $800K over 3 years. And all of that work is now under review from Nature Communications out of a small lab at Morehouse College. These types of things would not happen without the center. So for 2024/25 goals, we want to continue our Scholar in Residence program, which I'll talk a little bit later. We're actively writing a journal article on how other HBCUs can do what we're doing. And then we also want to build a pathway for sustainable funding for the center. So myself, Kayla, Dr. Sue Yan, who is the director, and Ms. Lowe and Ms. Chandler have been actively pounding the pavement for funding to continue this great program. One of the other things that we wanted to also do is to increase student engagement. So here are the pictures from the 2024 Quantum Engineering Workshop at NSBE. We just had a fantastic workshop in the great city of Chicago, which also had just as many students that were involved in that. Our students were also involved in Harvard's Quantum Noir, which we don't know when that'll happen again, but it's okay. We'll make that happen pretty soon. And then the other thing is that, again, we are focused on research, right? So there's a list of many of the papers that have been funded in this space. We've engaged 900 HBCU students through hackathons or coursework or direct research activities on IBM systems. We've also have, that number is changing, but we have more now than 7 students. It's probably around 10 that are in QISE specific graduate programs. And the biggest thing that we've done is we've empowered HBCUs with the small investment that was made by IBM to 2.5 times-ish to bring more funding to other HBCUs in that space. So this is a journal article that we've had on the cover. This just gives you a list of the awards that have been funded at other HBCUs after our initial investment in the seeds. One of which is a program that I run at a UIC that has Southern, Morehouse, and Spelman as a part of it. This shows you some of the numbers and shows you some of our graduates. So we've had NSF, GSR, FRP people that have gone to UCLA. We've had a couple students that are at University of Maryland. We've also had Victoria that's at Harvard. Our postdocs that are in the system, they get jobs as far as faculty and other places. And special shout out to one of our graduates this year. She's going to Rice University in the applied physics program there. I'm a product of that program. It is probably the best program for quantum in the world. Our students just don't do graduate programs. So they get hired by IBM and other places because one of the things that we want to do is just to support our students in whatever endeavor that they want to go in. And then this just shows you some of the things that other places can do. One of our focuses is engaging in K through 12 programs because quantum is about 25 years away. So that's something that we really want to do. And then number 2 is that we want to invest in Black faculty and future Black faculty to serve as role models in this space if they're at HBCUs or otherwise. North Carolina A&T has gotten a lot from us. Dillard has a program where they support 100 high school age young female students, and we continue to support that. We also have the Scholar in Residence program, where Dr. Zai was our first one at Spelman. We intentionally put them at Spelman to work on gender issues in QIS. And then you'll hear later today from our Scholar in Residence at Howard University, which is Professor Musa Noam, that will talk about great things that he's doing in optics. Now, that said, I won't take any questions for the interest of time. But what I will do is that I will introduce our next speaker. So as I said previously, We are lucky enough to have one of our board members here, Professor Serena Eley and Eley. I always know her as Serena because she's known me forever. But she is got her PhD from University of Illinois Urbana-Champaign. Her professor there is actually on the National Quantum Coordination Committee. Professor Nadia Mason. She's had a storied career. Serena's had a storied career working in magnetism as an experimentalist. And also, Serena started her career at Colorado School of Mines. She's now in the ECE department at University of Washington. She's had an NSF Career Award. She's also two of the five people. I'm sorry, she's actually one of the five people, the best person to ever get the AIP NSVP Joe Johnson Award winner. I said two because she was the second person to win it. She was much better than the first person to win it. And then let's see what else is great about Serena. Oh, Serena loves mountains and she loves to hike. And if you ever see her at a physics conference, she will be running. Not running away from you, but like running for exercise because she's one of the runners. So we're very, very happy to have Serena today. I don't know what I was showing the Women in Quantum series thing. Sorry. This. So we're very, very happy to have Serena as a part of the Women in Quantum series because I think she exemplifies what we want from all of our students. Last quick note, and I'll let Serena talk, is that Serena actually, so she's never been to Howard. So all Howard students, please show Serena around, be nice to her today. And secondly, you did a summer program at North Carolina A&T. Oh, okay. So she'll talk about that. Okay, awesome. But please, we're very excited to have Serena share her story, but also the great research that she's doing at University of Washington. Thank you all very much.
So I'm going to start off talking about my academic journey, which is going to include pivotal moments that led me to quantum, key decisions, and then I was also asked to speak about challenges. Don't have too much time to do that, but I'll highlight the major challenge here. The field of experimental quantum research is very resource heavy. It requires There we go.
There we go.
So liquid nitrogen's at 77 Kelvin. So discovering a superconductor with a critical temperature above 77 Kelvin meant that we could very easily cool down. Nitrogen is easy to use. We could very easily achieve superconductivity. And this really made it superconductivity considered to be more useful for applications. Okay, so as I mentioned, I knew at a very young age that I wanted to pursue superconductivity in the future. So in middle school, I first kind of started to think about what my career plan would look like. Okay, obviously the next step would be go to high school, graduate from high school, enter college. I knew that in college, it's very important to, at the beginning, create a 4-year plan. You look through all the possible courses you can take, and you're very strategic about what courses you take. And you include in that 4-year plan a series of summer internships to gain experience in different types of work environments, maybe different fields, to really kind of focus on, determine what you'd like to focus on. I knew I'd have to earn a bachelor's in physics, and then superconductivity seemed really complicated. Must enter grad school, get a PhD in physics. And then I pictured that I would like to pursue employment at NASA or a place like Bell Labs. So that was the plan. So now let's see what actually happened. Starting from the beginning, I was born right in the center of the country here in Omaha, Nebraska. And then in elementary school, very early on, I moved out here. I grew up in Fairfax County. For high school, I went to Thomas Jefferson High School for Science and Technology. It is a great school. I absolutely loved it. It's excellent for anyone, in particular for anyone interested in pursuing science and engineering. And then after my junior year of high school, I did my first summer internship through a program called NASA Sharp Plus, where I was stationed at North Carolina A&T in the mechanical engineering department, learning different techniques to measure, to detect damage or delamination in aerospace structures. After that, went back to high school, graduated from high school. And after my senior year of high school, I did an internship at NASA's Jet Propulsion Laboratory in astrobiology. And then I started the physics program at Caltech after my freshman year. At Caltech, I did an internship at NASA Ames, testing infrared detectors. These must be cooled down to reduce the noise so that you can detect strong infrared signals. And then you must also cool down the accompanying electronics. So I tested how basic resistors operated at low temperatures. They're no longer ohmic. And it was really during this internship that I learned that I liked the mechanics of performing low temperature physics experiments, which confirmed my interest in working on superconductivity. Okay, so then after my sophomore year, I split the summer. I did an internship at Raytheon Infrared Operations in Goleta, California, testing infrared focal plane arrays. And then I spent a month at the National University of Singapore fabricating superconducting Josephson junctions. And that's where I learned that I like to do nanofabrication of devices, which is necessary for the research that I do now. The following summer, I also split the summer. I spent about a month and a half at the Harvard-Smithsonian Center for Astrophysics doing computational astrophysics. I learned that I did not like the mechanics of doing computational astrophysics. And then I went out to the Max Planck Institute for Physics in Munich and worked on particle physics. Now, the year before, I had been working with this team I'd led this team to design an experiment that we would run in a microgravity environment through the NASA Reduced Gravity Student Flight Opportunities Program. So we flew out to the Johnson Space Center to actually run this experiment on the KC-135 aircraft. It flies in this parabolic path, such that at the top of the parabola, you experience a few seconds of microgravity. So then you run the experiment during those few seconds. Returned to Caltech and graduated. And then after I graduated, I got a Henry Luce Scholars Fellowship to spend 1 year in Tokyo, Japan, working at the Superconductor Research Labs, where I learned how to fabricate superconductors under high pressure. After that, I went out to Strasbourg, France to do a program at the International Space University. When that program was finished, then I had already applied to grad school, I had gone into grad school, and I had deferred. But I was offset with the semester system, so I needed to get a job for several months. Went back to Raytheon Infrared Operations, tested infrared focal plane arrays for several months, and then started the physics PhD program at the University of Illinois, Urbana-Champaign. Honestly, I wasn't very excited about moving out to the middle of Illinois, but I was excited about working at the University of Illinois because it might sound cheesy, but really it felt like walking in the footsteps of John Bardeen. John Bardeen had performed quite a bit of his work there. He's won 2 Nobel Prizes in physics, one for the invention of the transistor, and the second was for development of a theory called the BCS theory, which describes the microscopic origin of superconductivity. At the University of Illinois, I worked for Professor Nadia Mason, but she had not yet arrived there during my first year. So that summer, after my first year, I did another internship through a program called NASA Academy. There I was stationed at NASA Goddard in this area in Greenbelt, Maryland. And in that program, they had us travel to different NASA centers to really try to understand NASA's mission goals, how the mission goals differ between different centers, and we did a little bit of research. Then I returned to the University of Illinois, formally joined Nadia's group, helped to build the lab, and then did not need to do summer internships after that. After I graduated from the University of Illinois, PhD in physics, I started working at Sandia National Laboratories, building labs to test silicon-based spin qubits. Then I moved a little bit north and got a postdoctoral research position at Los Alamos National Lab, studying vortices in superconductors. At the end of that 3-year term, the question was, do I stay? Do I try to stay at Los Alamos National Lab or in general at national labs? I really did like working at national labs. They have lots of resources. I have a lot of collaborators still at national labs. But then I decided to try academia. I like the idea of getting startup funds to start a lab right away. So I started a professorship in the Department of Physics at the Colorado School of Mines. Mines really is a great school, especially for undergraduate education in the sciences and engineering. They really heavily focus on this. They do great research also. Their clean room, though, is a little bit small, and my work does require fabricating nanostructured devices. So I decided to move to a larger university that had a larger clean room. So here I am now at the University of Washington in the Department of Electrical and Computer Engineering. So that wasn't quite what I pictured my career would be like, but what's next? Hopefully I'll be at the University of Washington for a while. That would be nice. Now let's look at what type of work I do at the University of Washington. Okay, so here is my lab, the URL for my research program. One of the overarching themes of my research is that we look at the effects of material disorder, so disorder in the crystalline lattice, on the electromagnetic properties of quantum materials and some devices. Regarding what types of quantum materials, we predominantly study superconductors, where we look at vortex dynamics in superconductors. I'll try to quickly highlight some of that work later. and also study energy loss mechanisms that affect superconducting quantum circuits. I don't study qubits, but we do study circuit elements that are important for quantum circuits, such as resonators and superconducting Josephson junctions. We additionally study magnetic materials with a focus on skyrmions, a type of magnetic vortex, and I'll try to quickly highlight a little bit of our skyrmion work. As of now, this is my research group. I have 5 graduate students and 1 post-baccalaureate who will transition into a graduate position in the fall. So basically 6 graduate students and only a couple undergrad researchers. I hope to expand on that. I typically have more undergraduate researchers. My group is interdisciplinary. I have students from physics, electrical engineering, as well as material science. My lab is in the Paul Allen Center for Computer and Electrical Engineering at UW. And we have 2 main instruments. One is a magnetometer. And in the magnetometer, it's very nice. We can measure samples of different forms, so tiny crystals, thin films, liquids, powders. We don't have to attach wires to the sample. It has a magnet, and we can basically induce a current or a magnetization in the sample. When that sample is translated up and down between some coils, the voltage in those coils will change based on the signal from the sample. And then it can tell us what that signal is. And for the magnetometer, we can conduct measurements down to 420 millikelvin using a helium-3 module. We additionally have a system for electrical transport measurements, which is a fancy way of saying collecting current voltage curves, measuring resistance at different temperatures and fields, down to, it's actually about 1.5 Kelvin. We have space to store samples, a fume hood to do a little bit of sample fabrication, and then a lot of accompanying electronics. Our work depends on a lot of tools, so we have to use shared facilities. Adjacent my lab is the UW Quantum Technologies Training and Test Bed. We call it the QT3 lab. And for my group, the highlight of that lab is a blue forest dilution cryostat, where we can conduct measurements down to about 10 millikelvin. And a student of mine is finishing helping set that up pretty much now. So I'll see when I get back whether or not that has been successfully commissioned. We also use the clean room facility at UW to make our devices. Regarding methods, this is kind of the typical flow of a lot of the projects in our lab. We'll start off growing samples or getting really high quality samples from collaborators. On some samples, do some nanofabrication. Then we have to understand the crystal landscape of these samples, so we'll do some microscopy. And we then spend most of the time using the instruments in our lab to perform electronic and magnetic characterization. We can determine different magnetic phases. Is it a ferromagnet, a paramagnet, a diamagnet, superconductor? And then there's a lot of information that we can extract about the dynamics of vortices, which I'll talk about in a second, skyrmions. So we then will do some analysis to understand the physics associated with these measurements. And oftentimes we'll then tune the microstructure, study the modified landscape, and then see how that changed the electromagnetic properties. For some materials and devices, it would have gotten better. And in other cases, we're just trying to understand the effects of these defects that are inherent to all materials on the different phases. Okay, so now I'll try to, with the remaining time, I'll try to highlight 2 projects in our group. And I'll start with vortex dynamics and superconductors. Okay, so first, I've told you that superconductors can carry a zero resistance current, so no loss to resistance, and they can only carry this, we call it supercurrent, up to a critical value, JC, and the critical current density. If the current surpasses that, then the material becomes normal. It is not superconducting, so now it has resistance. So for power and magnet applications, the goal is to maximize JC. So then we have to understand, what does JC depend on? And JC is heavily affected by the motion of something called vortices in the system. Okay, so what are these vortices? If you apply, or if a superconductor is exposed to a small magnetic field, it will completely expel magnetic flux. This is unusual for many materials. The magnetic flux will pass through. Here it expels magnetic flux. This is called the Meissner state. If the field surpasses a critical value, we say it becomes thermodynamically favorable. So at this point, magnetic flux will penetrate through the material in the form of bundles of flux called vortices. So what you can picture is that we have these discrete, or these separated nanoscale regions. You can picture an array of these separated nanoscale regions where the magnetic field is penetrating. And these regions are non-superconducting. And these are called vortices. So if these regions are stable, then they don't cause a problem. But vortices move around because they're pushed by currents. And then they also hop around due to thermal energy, just from having non-zero temperature. So they end up being a source of energy loss. So we have to figure out how to slow down the motion of these vortices. And I'll tell you how we do this in a second, but let's look at applications of superconductors quickly. Superconductors are used in a range of applications, and they're being designed for a range of next generation applications. So this includes power cables, surge protectors, low dissipation classical computing components, as well as quantum computers, gamma ray detectors of clandestine nuclear materials, MRI magnets, particle physics, magnets, accelerator magnets for particle physics, magnets for fusion, sensors for X-ray astronomy. So a wide range of applications, and in all of these applications, when designing the materials, we must consider the dynamics of vortices, how to slow down vortices when we're designing these materials and devices. And here are the benefits. So if we're successful in designing the materials in a way in which we can slow down the vortex dynamics, some of these superconductors can carry extremely high currents. For example, this one, YBCO wire, can carry 100 times the current of copper wire of the same size. And here's an example of the result of this. So here you see a superconducting motor. And this depicts a YBCO motor, 36.5 megawatt motor. And then by comparison, this green box depicts a 21 megawatt copper motor. So the superconducting motor ends up weighing less than half the size of the copper-based motor, half the weight of the copper-based motor, including the weight associated with the cooling system of that's necessary for the superconducting motor. So then basically what all of this text here says is that when weight and size considerations are important, then sometimes superconductors may be your best or your only solution. Okay, so our research problem here, I told you that vortex motion introduces energy loss that can result in keeping the critical current low. It causes energy loss in superconducting circuits and also causes noise. The way to slow down vortex motion is actually to make the materials dirtier, to add defects to the materials. And those defects end up being, you can think of them as an energy well in which the vortex wants to sit to minimize its own energy. We call it pinning. So it can kind of immobilize that vortex. However, it's very challenging to come up with the optimum defect landscape. What are the optimum types of defects for a specific superconductor, as well as what's the optimal defect density? So in our lab, we study a very wide range of superconductors. We determine the current carrying capacity, JC, in these materials. We can look at the rate of vortex motion. and then draw correlations between that and the types of defects in the material, as well as correlations between that and material-dependent properties like the critical temperature. The overarching goal is then to come up with kind of a prescription for what the optimum defect landscape would look like in a range of superconductors. Right now it's trial and error. You add defects and then you see what comes out and then try again, see if you made things better or worse. So we want to kind of come up with a prescription for looking at these different material properties where you would kind of know what the optimum disorder landscape should look like. So then how do we tune the defect landscape? There are a number of ways to do it. I'll highlight 3. One is to introduce defects through particle irradiation using an accelerator. So here you can see a transmission electron microscopy image of an yttrium barium copper oxide superconducting film that was bombarded with oxygen ions, and all these dark spots here that you see are 10 nanometer size defects that were introduced. And what you see in this plot here, this shows JC versus temperature. At low temperatures, we nearly doubled JC by bombarding the sample with oxygen ions. We irradiated a superconducting niobium diselenide crystal with lead ions at a very high energy. And what you see here, these dark stripes, are amorphized tracks that were introduced through the irradiation process. This plot shows magnetization versus field. You can think of the magnetization as being proportional to the critical current. And if you just focus on the top half of this graph where the magnetization is positive, this green curve shows what we measured before the defects were added. And the blue curve shows the dramatic increase in JC after adding defects. It's hard to even quantify how much it increased. We were barely able to measure it before adding defects. A second way of tuning the defect landscape is to add impurities to growth precursors, such that non-superconducting inclusions form in your superconducting matrix. So in this image here, you see non-superconducting barium zirconium oxide nanoparticles that grew in a YBCO film, these dark spots here in this TM image. And then here you can see JC versus fields. And again, we nearly doubled the current carrying capacity by adding these defects. Lastly, you can, through nanopatterning, you can tune kind of this energy landscape that vortices see as they're moving through the material. It has become routine to pattern an array of holes in the ground plane of superconducting circuits to trap vortices away from operating currents. For superconducting resonators, this does result in a dramatic increase in the quality factor, which is a measure of energy loss. And it also will decrease energy loss in superconducting quantum circuits. Okay, so lastly, I'll tell you very quickly about skyrmions and what our skyrmion research is. So first of all, conventional electronics is based on transport of charge carriers. So when you're thinking about with conventional computing, your 1 or your 0 bit, that's going to be based on transfer of charge. You might think about a capacitor being charged in one direction versus the other. Now, control and measurement of spin is predicted to require less energy. So computing that's based on spin, that field is called spintronics. And then in the field of spintronics, you have to determine what you want to use as your information carrier, what type of spin structure one would like to use as the information carrier. And skyrmions are a candidate for this. And the skyrmion basically looks like this. It is a nanoscale spin structure that looks like a vortex. So for the case of conventional computing, if it forms one particular arrangement, then it could be a bit like a bit 1. And then if it whirls around in a different direction, it would be a bit 0. We call this topological charge. So if it has different topological charges, then you could use it as different computing bits. And then there are predictions that it requires very little currents to manipulate skyrmions, but a lot of work has to be done to understand their motion and their formation. So if we want to use skyrmions as information carriers, we need to be able to read, write, and delete them. We need to understand how they interact with defects in materials. Defects are inherent to all materials. We should be able to control their motion with an applied current. So skyrmions are kind of like soccer balls. You know, if your soccer ball is spinning and you kick it, then it'll move in a curved trajectory. We call this a Magnus force. Skyrmions also experience a Magnus force. So in response to a current, they'll move in a curved trajectory towards the device edges, which is not optimal. So our goal is to study how skyrmion formation and motion is affected by different types of material defects that are typically inherent to our samples, determine if we can control skyrmion trajectories by adding defects. Perhaps we can prevent them from collecting at device edges. And to do this, we apply a very similar method that we do with the superconductor vortex project, where we can add lots of different types of defects and then see how the skyrmion properties change. As a quick highlight of recent results, we irradiated an iron germanium film. In crystalline, kind of clean iron germanium, skyrmions form. When we irradiated the film, we introduced an array, we introduced these amorphized regions and ended up finding out that anti-skyrmions, which are the antiparticle of skyrmions, ended up forming in these amorphized regions. So we created this system that has these skyrmions and these anti-skyrmions. And the usefulness of this is that they could serve as two different bits, a 1 and a 0, in conventional computing in spintronics. So they're of interest for that. Okay, so that is my time is up. I'd like to thank you for your attention, thank my group's research funders, and ask if you have any questions.
So my question is, what does JC stand for?
JC, that's an excellent question. JC stands for, specifically for critical current. But how you should think about it is that all materials have a maximum current that they can carry. So you know, if you touch a wire, so sometimes it gets hot, like a light bulb can get hot. That's associated with resistance. If you try to pass a higher current through that wire, it could end up melting. So then you surpass its current carrying capacity. So just like something like copper, which is non-superconducting, has a current carrying capacity, our superconductors do too. Basically, once you hit JC, then first they're good, and then after that, they're going to stop superconducting. They'll get really hot.
Thank you.
Thanks for your question. What's your name? Kinsey. Nice to meet you. Thanks for coming to the talk. Other questions? Yes.
So recently, in the past few years, there's been a lot of studies about room temperature superconductors. You know, I was going to ask this, but you being an expert, what is your take on room temperature superconductors, particularly under high pressures? How realistic is that? And also, how far away from breaking these critical milestones to getting something close to a room temperature superconductor?
Okay, that's hard to say. Yeah, that's like the scandal. The scandal of condensed matter physics is room temperature superconductivity. So in some cases with these discoveries, as you probably know, some cases are just fraud, unfortunately. There have been some cases where, honestly, the research was going through the normal scientific process where it appears on the archive. The researchers were not terribly knowledgeable in the field of superconductivity, but somehow the study made it into the media, so it was blown up before it went through the scientific process. The challenge with studying superconductors is that, okay, so zero resistance means when you're applying a current, you measure zero voltage. That's the same thing that's going to happen if your sample's broken. So in the field, we have to be very careful about going through, and there are certain metrics you would measure a transition from a resistive state to a zero resistive state. You can use like the magnetometer we have to measure the Meissner effect, confirm that you have the Meissner effect diamagnetism. You can measure a jump in the heat capacity. You can measure IV characteristics that show you transitioning through this IC or JC. And these are kind of the things that you have to do to show that you have a working superconductor. So then the issues with, superconductors under high pressure. In some cases, the materials have to be still held under high pressure for them to superconduct. So that's going to be application limiting. It's not just, we focus so much on critical temperature because of this idea, if the critical temperature is room temperature above, then it would be wonderful. We could have power lines, right? Or that we don't have to cool, that would superconduct. However, if JC is really, really low, because vortex dynamics are really fast, which we would expect they would be at room temperature, then at that point, the superconductor isn't necessarily that useful. So it's a lot more than just room temperature superconductors. Regarding how close we are, I don't know, sorry. But yeah, there are a lot of parameters we have to consider, more than just the critical temperature.
It is possible though, right?
We will see.
Thank you.
Yes.
What made you want to choose UIUC for your graduate school?
They have a really strong condensed matter physics program. At the time, they were ranked #1 in U.S. News and World Report. So it wasn't just John Bardeen that was there. So I knew that Bardeen was there. Bardeen, Cooper, and Schreifer came up with the BCS theory to describe the origin of superconductivity, how these electron pairs form. And because of that, it was basically a lot of people ended up gathering who do low temperature physics, ended up gathering at UIUC. So lots of research options, strong collaborations internally, a really nice infrastructure, probably one of the best. It ranks probably in the top maybe 5 clean rooms, like shared facilities that I've seen in the country. So, other questions? Yes, please.
You mentioned that you had an idea of what you wanted your career to like when you were in middle school. But could you talk about like what the years before middle school like happened to you to be that prepared?
I think this is a great area to grow up in, honestly, because there's a lot going on in this area. You see that I did a lot of programs at NASA centers. I remember NASA Goddard had a lot of events. So it was important to go out to those events at NASA Goddard. The Smithsonian Museum, spent a lot of time at the Air and Space Museum, Museum of Natural History. And all of these are free. It's very easy to just go see the new exhibits. So it was that type of exposure. Also at the time, I'm not sure what's replaced it, but the Washington Post had the mini pages, which was the newspaper for kids that came along with the Sunday Washington Post. And when that would arrive, then my parents would always pass that along to us to read. And they had a lot of articles also about the sciences. So I think just that exposure was really, really important.
And then I have one last question.
Yes.
So for those that aren't aware, Serena is one of less than 100 Black women with a PhD in physics. And do you have any advice for the next 100 PhDs in physics?
So this might look a little crazy, but I think like going after all of those opportunities was it just built up more and more excitement. Like even if, okay, sure, computational astrophysics wasn't my thing, but I enjoyed having that experience and now have an idea of what's being done in that field. So it's actively, I think it's really important to go after those opportunities. Certainly as an undergrad, every single summer should be spent doing work in the field. But before that, if you're not, certainly not able to get internships when you're, in elementary school, but you can go out to these science events, do science camps, go to the exhibits, spend some time really focusing on a few of them, trying to read and understand what's going on in the field. So I would just say, just be aggressive about that.
I have a question from one of our scholars.
Yes, please.
Denmark Elisma. He says, Dr. Eley, has there been any major setbacks during your scientific career?
Okay. Setbacks. Yes. Oh yeah, I'm trying to choose which one. What setback? The biggest setback I've never talked about publicly really was when I was at the University of Illinois after my first year. I was diagnosed with bone marrow failure. And it was very rare. It's like called aplastic anemia and PNH, and like, I don't know, 300 Americans a year get this. And it was really at that point a question of, what do I do? Like, I was really slow moving around. Do I keep going, or do I need to change paths? Because I went out to Johns Hopkins to kind of discuss the situation. They did the official diagnosis. And it was, for them, they're like, hey, there's a 30% chance this thing is just going to resolve itself over time. 30% chance you'll need a bone marrow transplant, and 30, so we'll see. So at that point, I thought about like, well, what I really want to do is physics. That's what I've always wanted to do. Why change paths now? And at that point, it was really nice to be at the University of Illinois, because the head of the department was like, John Stack, he's like, this isn't a problem. Don't worry about it. He's like, if you need to move exams around, hey, we're going to push back your qualifying exam by a semester to give you some time to adjust to this, which was great. And I'm totally confident that you're going to be able to graduate. This won't be an issue. We'll support you. And being in that, and my professor, Nadia Mason, was very supportive. So at that point, I'm like, great, I'm moving a little bit slower, but I will adjust to it, and just kept going. So that was good at this point. Okay, thank you.
All right, so now we're going to move into our Watch and Learn portion. From our IBM HBCU Center scholar in residence, Professor Moussa Ngom. He's from Senegal, that's why he's so tall. But he is a fantastic science and collaborator, expert in all things light matter interactions. Twisted light is something that he'll talk about today. He's building some stuff downstairs, so if students are interested in getting involved with that, please talk to Moussa a little bit about that later. And in the interest of time, I won't tell you all the great things about my good friend and colleague Moussa. I'll let him tell those on his own. So without further ado, Moussa.
Thank you. Michele, I blame you. You always have me speaking of such great speakers. So I don't, that was a wonderful talk. It was absolutely wonderful. I thought I traveled a lot. But you, my friend. No, this is going to be my default picture from here on out until things are better for science. Yeah, so I designed my talk today to argue, to convince you that we need to build a quantum center here, a center for us, so that all of these great scientists that are all over the place can come here, whether they work here or not, but can come here and use this as a tool. Okay, we go from there. So one of the motivation I have, these are two mentors that were introduced to me, by the way. He was my advisor, Herb Winful, at the University of Michigan. And this is Professor James Schaefer, who is an architect. And he, the reason why I use them as mentors and as example are, these are some of the smartest people I know that have been the first in their field to do something wonderful without having the price and the recognition. And I'll tell you why in a little bit, right? So, for example, a lot of people do not know that James Schaefer is the one that actually came up with the idea of the Martin Luther King design. He was one of the first full professor of architecture, Black full professor of architecture in the country. He's at the University of Michigan. He's retired now. He's writing books and all of this other stuff. But this thing that we all love is his idea, and he's the one that put it together and hired the people, or chose the people that want it and tell them what the design want to, and chose the rock, and so on and so forth. But nobody really knows, right? These are the ones that we should design centers around. Herb Winful. Herb is a physicist, right? He does nonlinear optics and everything. So the Nobel Prize in Physics in 2018 by Gerard Mundru, all the theory that was developed in that paper was done by Herb. His prize was to introduce Gerard Mundru during the Nobel Prize winning thing. He's the one that introduced him in Switzerland, but they didn't give it to him. We should build a center around Herb. These guys, they're retired now, but we have so many of these stories around. So many of these stories. That could be any one of you. The one thing we know is most of the time we're the only one. I bet you in your travel, you might have been the only one there. Especially Black women, right? So that's what I'm trying to talk about here, okay? And we've been having this conversation with a lot of very smart colleagues. And then out of all of my mentors, I met this guy, okay? And we've been talking about this all the time, right? We talk about soccer, like half of our conversation is soccer. The other half is how do we put our ideas together, right, to build a center around what we know? We are both optical physicists. We're both passionate about it, and we want to do something. We want to have an impact, right, on just quantum photonics and everything, including what Eric is doing, for example, those kinds of work, right, that we need to put ideas around. So I believe the center here should be personally around photon, right? People say quantum photon, you say all the photons are quantum, but you see what I mean? Photonics, single photon, entangled photon, and all that it could do, including, I'll talk about some of the photons that we can create that can interact directly with the skyrmions and direct them in different places that we're trying to do, right? Rather than trap them with defects, for example, you can use light that behaves just like the skyrmion, so you can put it in one place and keep it there. So it doesn't add any more losses. All the losses that it has gets transferred to the optical beam. Those kinds of things that we can kind of design here to do, okay? So transfer knowledge. All of these pictures to say, we have the people, we have the intellectual capacity, we have the students, we have everybody that is eager to do, right, to transfer this. And I am convinced that the place to do that is here, Howard University, okay? And this is just further argument about all of the people that we have. Whenever we meet, we have these conversations, and those are the only time. We do this once a year. We should be able to have these sorts of talks every month so that we can always, because by just listening to her, I've had ideas to redirect part of my research. Like that's what it would do. It would just make us smarter all the time, exchanging of ideas. This is where the argument gets a little bit iffy, because I think I am personally convinced that for the quantum internet to work, so this was paper, all of the major quantum people all over the place, right, from Harvard, from all of these things, right? So before I even get there, Thomas said something about the success story being this, your student going to Harvard. I want to convince you that we can build something here such that the success story would be a student going to Harvard to get their PhD. We are able to do that. So the quantum internet. So I'm convinced, right, everybody's working on different things, the quantum sensor, the quantum repeaters, everything, right? So, but for all of these to happen, right, for all of these different quantum systems to interact, they must use photons. They must use photons, but not any photon. You have to create photons that can interact with the quantum system. If you've taken any sort of quantum mechanics or heard anything about what people talk about quantum mechanics, if you have a quantum state, if you shake it or disturb it, you lose its quantumness, right? You lose its quantum properties. So whatever you've encoded within that quantum properties will get. Now, can we create photons that could actually interact with the quantum system without disturbing it, but at the same time getting information from that quantum system to transfer to a different quantum system? Something that we can do. And my research personally is within this quantum frequency conversion, where you have different properties. You get a single photon that gets properties from something, but because photon also interacts with everything, you encode it into so many degrees of freedom so that one of them will get transferred to the next system, right? Without actually losing all the information you have, okay? And I think every time we get together, I show this picture. I've talked about my work and everything and all of that. So basically, in very short, my work is any optical design that you have, any optical setup that you have, we are able to turn it into a mathematical expression. So that if we turn it into a mathematical expression and we understand how it interacts, any sort of material or anything else that you want light to interact with, we can have a mathematical interpretation. But more importantly, we can actually control the interaction. So that's what my work is. And this picture, and from there, we've done things like, we try to work on things like sensing, for example, measure blood sugar content without actually poking yourself, right? Is there a way to do this? This is actually work that I show this picture because it's beautiful. It's from Kimani Tusa. He was at, I don't know if you know him, some work that they're doing and that we've done as well and published as well. But for what I'm talking about, what we do is, if you understand how fiber optics work and how we, all of the fibers that are underneath are single mode fiber. That means only two kinds of photon can get transmitted, right, with different polarization. Is there a way to increase that capacity by making light not just have polarization, but also have other degrees of freedom? For example, light rotating or orbital angular momentum light or things like that that can propagate inside fiber. Because you will see that if you want to create quantum light, they tend to have those properties. We have to be able to take that we've created and propagate it with what's in the ground, right? Because we're not going to dig the ground to add more fibers. Whatever we design, we have to make it with what is the infrastructure that is already here. Okay? So that's one thing. Another thing that we've done, another tool that we've done with light, you can do what is called filamentation. Filamentation is a nonlinear property of light with which you actually can have very intense, very fast, very fast light is basically light that can deliver at a short period of time a lot of energy, like enough energy to, like from the sun in the day within a femtosecond, for example. If you do that, you change the environment. If you change an environment, the environment in turn is going to change the light. So what we've learned from that is if we use filamentation and propagate it through space, you can actually create within space transmission line or that are similar to fibers, but in space without actual the fiber within which you can actually couple light and propagate from here to space. For example, these could be relevant when it's a cloudy day like this and you want to transmit information from here to a satellite, from a ground station to a satellite and so on. So work like that we've done. In the quantum regime, also just manipulating light, we are able to demonstrate methods in which we can create quantum light. It's the best word I can find. Down converted light, single photon, entangled photons, and things like that, but with much, much higher yield. Okay? All of these from just our computational optics, from just taking an interaction that people do, and by manipulating it, improving the result and creating new results. What I want to do in combining all of these methods, I'll take all of these methods, and we want to combine them into generating a system with which we can create, we can have, you give me a pristine material or material with defect or something, and then we can probe the material, create defects, create single photon emitters in that material so that we can have different emitters. Each one of the emitter will emit an exact, so when I say single photon, I need to precise that. Single photon, that doesn't mean that it's just one photon at a time, right? It's still a photon beam. It's still a light beam. But in that beam, every single one of the photon is the same exact photon. It has the same polarization, the same energy, the same everything. Okay, so it might as well just be a single photon. Okay, that's the idea. So imagine now we have a material, for example, a two-dimensional material. So one of the single photon emitters that it's a very popular research now, where people can make a defect within a two-dimensional material. Cool thing with two-dimensional material is supposed to be a single layer of atoms. So if you have a pristine one, for example, that filament that I was talking about could be very small. It could be nanometer size, right? Way below the diffraction limit of light. Okay, and then we can knock, for example, a single atom out of a two-dimensional material. So what will happen is that atom that was connected to the other atom will be dangling there by itself. So if that atom is dangling there by itself, you can probe it really, right? You can set it up with light. You can say, okay, I want this atom to have this energy to vibrate at this energy. And every time I want to learn something about it, I hit it with a single photon to get exactly what I want to get from it. That's what I work. That's my dream in building, and that's what I'm working on, for example, right now at RPI. So we use three things. So I have to go here. My voice is loud enough. The pump is the filament. Okay, we can probe it with a single photon, and this is timing. Everything here is pump probe. Everything is timed. We know exactly when to get it. We know exactly when to probe it. And the idea here is to probe it so that we can only generate single photon. And then we can take those photons. Okay, we can demonstrate that they are exactly single photon, and we can demonstrate that they are also correlated or entangled. So you hear about entanglement. I'm sure by now everybody knows entanglement. It's this idea that you can create two particles, okay, two quantum nodes, right, two quantum systems from the same structure, such that they are correlated, such that they have this connection either in energy, in polarization, in spin, for example, for electron, such that, and no matter how separated, such that if you have any interaction with one, the other one will, in a way, know almost instantaneously. And you can encode information within that. Okay? You can do that with photons. So electrons, you do it with spin. Photons, you can do it with polarization. You can do it with energy. And you can even do it with the phase of the photon. Okay? And if you have photon that has some sort of structure to it, you can actually do entanglement in spatial structure for orbital angular momentum. So we have greater flexibility with photon. Okay? And I'll repeat myself again. The reason why, I'll just put up both of them. So when I teach quantum mechanics, the interaction of light with matter, single photon with an atom, is always described. You can use a harmonic oscillator to describe how it works. So you basically create a vibrational state. That's what causes heat. That's why you cool down things so you can reduce that vibration. Another way to reduce vibration, reduce all of those heat and all of those extra errors, is to use a single photon. So that I reduce the intensity of it. Right? You only have one energetic vibration that reduces that. That's why we are so interested in single photon. Okay. A pure condensed matter physicist will tell you the only way you can generate true single photon is by using a single atom, cooling it down, and then probing it so that you only have one single transition, and that transition is always the same. You excite an atom because you're cooling it, it wants to go back to its initial state, to its ground state. When it does that, it releases energy from a photon. If you cool it so that you only have a single transition, that transition will always going to be the same, so the energy will always be the same. So the single photon beam for that is the purest you can get. But as you can imagine, if it's a single atom, this is very weak. It's beautiful to make. Every time you have something like that, it's a Nature publication. However, right, it might be completely useless because by just coupling this to a fiber or something, it's all gone, okay? The other method is what I was just talking about, to use a two-dimensional material that is really very similar to this, but the difference is you can do it at room temperature. So that you don't have the cooling, all of the big system, all of the cryostats and everything. All of these you can do at room temperature. And that's where we want to be. Initially, we use TEM, transmission electron microscope, to do, because TEM use electron, and you can have enough energy to actually just create a single defect. Okay? What we want to do, so whenever you do something, you have to go to the state of the art and compare your work to the state of the art. The state of the art is using transmission electron microscope to create a single defect, the single atom, so that we can probe these, for example. What we want to do is, can we compare the laser system that we have here? We don't have results yet, we're working on it, but can we compare these defects that we make with our laser with the state of the art? So the laser is we use Thai sapphire lasers. They're 800 nanometers. So the pulse energy is about 1.5 eV, so 800 nanometers, 1.5 eV. The energy of the actual system is about a few millijoules, 1.2 millijoules, I think that we have, due to the repetition rate of the laser. Okay. But it's not a single part. I just said, yeah.
What's that in milliwatts?
What is that in milliwatt? Oh, it's 10 watts.
10 watts? Oh, wow. Okay.
Yeah. Well, I mean, we reduce it. So when we interact with these, we use maybe 1 milliwatt.
Okay.
Yeah, but it's not. So the wattage is how many photons hit it. This thing is, we're more interested in the energy of the laser.
And so with 1 milliwatt and 150 femtosecond Thai sapphire is enough to create a defect HBM?
Actually, that would be much bigger than this. We're trying to reduce that. Yeah. We're trying to reduce that. Absolutely. That's what we're trying to do. Yeah. So, for example, let's say we've created this. What we have learned is how, when we have a two-dimensional material, when there is a defect, for example, we get sample from Serena, and she said there are a few more defects. With just light, without her telling us where the defects are, with just how the material responds, we can actually tell where the defects are. Once we know where the defects are, we can probe the defects exactly. Okay? Because that's what we will learn to be able to probe the defects that we've created ourselves. Okay? So, for example, in two-dimensional material, they have second harmonic responses. So, second harmonic is basically for each one photon that you put into the system, it interacts with this nonlinear material and give you another photon that is twice as energetic as the input photon. For that to happen in general, it happens in what we call non-centrosymmetric material. The way I explain it usually is that, like your hand, when light looks at it this way and looks at it that way, whether it's this way or that way, it's non-centrosymmetric. Okay, it's not, the light doesn't see the same. In that way, you can create these sorts of light that is twice the energy. For two-dimensional material, the way they are made, if it's a single layer, you'll get a very strong second harmonic response. But if it's two layers, for example, then you lose the center symmetry. And then, if you have, imagine this is a two different two-dimensional material, and right here they overlay, and you get response from the two-dimensional material on either one. But here we don't have a response. How do we manipulate the light so that even though this doesn't want to respond, we can have responses from that? Right? We can use the same technique from different part of the non-responding material to get light from. Because really, you'll hear a lot of people talk about dark photon and everything. It's not that light isn't there. It's that the light that is there is interfering destructively to not emit. And interference is all a phase process. So if you manipulate the light in phase, you can actually change, you can actually move the destructive process of it. Yes?
Yes, are you considering twist angles to have constructive versus destructive influence?
Yes. Yes. So we are actually, I didn't show it here because we want to publish it before somebody.
Oh, okay.
We are actually using light, like, so we have Moira structure, but it's not a Moira structure. We just have laid material, and we use light to twist them, and different angle we get different responses doing a pump roll with just light. Right? So we don't make Moira structure so it stays there. We do it with light so that it comes back all the time, so that you can have a tunable Moira structure, for example.
Do you know exactly the twist angle and all that and the correlation?
So yes, we can calculate the twist angle. So we can well, yeah. So because we don't have a TEM to, for example, measure it.
Okay.
So right, okay.
Not about TM, but another measurement.
Another measurement. Okay, perfect. Yeah. So what we do is, like I said, we're not with that condensed matter. We're not material physicists. What we do is we go to the literature and we say, if you twist it at this angle, this is the response that you're supposed to get. So that we put the light and we get that response, and we say, so if these guys are right, then we must have twisted it at this angle with just using light, and so on and so forth. And we build a table in that way. Okay, and this is just, and so that is just the response with two-dimensional material in creating a single photon with this to build our system around it. Another thing that we do as well is to generate structured light. When I say structured light, just like I explained earlier, is light that has some sort of structure to it. So most of the light that you see that is coming from all of these are basically just Gaussian light, right? It just comes at you flat like a flashlight and so on. Now imagine we can create a flashlight that can give you light that just doesn't come at you, but come at you differently, whether it's staggered, or it comes with a twist, or it comes at you at an angle, or it sweeps through. All of those are structured light, right? So when you have such a light, the way it interacts with this environment now changes, okay? For example, we are interested in vortex light, vortices. That's why when she started talking, you say, okay, I'll bring this up. So this is something that we create so that now the way we interact with light, if you've taken quantum mechanics, you could go spin orbital. So electrons that orbit, I always have to preface this. This is the wrong design for an atom, but it's beautiful. So I like it. So for the condensed matter physicists in the room, just in case. So the idea here is to have light that both interact with the spin of the material, but also with its orbitals. Okay, so you have two levels of interaction. So the electron of the polarization of light interact with this spin of the material, right or left, and the structure of the light coming at you in a spiral, right? Orbital angular momentum could transfer orbital angular momentum to the orbitals, right? Or take away energy from it because light can do both. It could add energy, but it could also take away energy. You can actually, if you hear this whole idea of light cooling.
If you have the right energy matching conditions. Right?
Yes. Okay. So threw me off. Okay.
Sorry.
Yeah. Yeah. So yeah, you can do that. So you can use light to interact with material. So the cool thing here is, for example, like she said, if you have the right energy to interact, right? So if, for example, the transition of an electron from one place to another, you only need to put 3 electron volts of energy. You can get light that can give you 3 electron volts. But that's just not what light does. That's why I hesitated, because you can do it non-linearly. It doesn't really have to be the energy of that system. You can have a very strong interaction, non-linear interaction that forces it to interact. Just like light is propagating linearly here, but if you focus it and to control it in a certain way, you can actually have a non-linear interaction that changes everything, and it has little to do with the energy of it or matching the energies. That's why I hesitated, okay? So we do all of that non-linearly so that we don't care about what the light is. We care about the energy of the light. 2 minutes? Okay. So in a way, in that way, what we have done, for example, is to use light to emulate, for example, electron spin. But since electron can be spin up and spin down and behave, and if you put it in a magnetic field, they will go in different direction. How do we do that with light? We have to create 2 different photons. Photons that couple until you uncouple them, but at the same time, they interact together. So we do this, for example, using nonlinear properties, nonlinear interaction between light and matter. Another thing that we have done, I was going to talk about the mathematical thing, but for example, the Dirac monopole. So I'll go through this really quickly. So Dirac stipulated that, for example, to create monopole, right? The vector potential that you need to input in the system has to be like a field that has a singularity in the middle. That means it's 0, right? You have phase of 0 inside, so you don't have intensity. So we create light that is doing this. So the light that I showed you with the vortex does something like this. But the reason why we cannot absorb monopole, because if you take the Stokes vector here, if you take the surface integral of a curl, you get 0. That's the non-existence of monopoles. Okay? I'm trying to hurry up and getting my words here. So what we can do in the lab, however, with light, is we can take the light that we have, we can do a Fourier transform, angled Fourier transform to give the light a different structure. We input it non-linear, and we can create what Dirac said if you were to create 2 monopole Dirac couple would look like. This is just a theoretical paper. This is something that we've done. We're publishing with Thomas. Some things like that we can do with light. All of these are non-linear interactions that we do, okay, with different material. And this, Serena said something about topological charge. So light could also have topological charges, and all of these topological charges determine the interaction between the 2 photons that you created, how they orbit, and how they interact. So these lights, as they propagate, they do this, as if it's a web, right? So those are the kind of, all of these things that it's doing. You can actually encode information in these properties as they propagate through and interact with things, okay? And I'll stop here. Some other.
We'll have time for one pressing question, and then we'll move over to lunch where you can harass the speaker as much as you want.
Yeah.
I do have one question again from Denmark. What are the challenges of creating a photon source?
Money, first of all,
Yeah.
because we are experimentalists. The kind of lasers that we need, patience. And what we want to do here, when a student join my group, the first thing I tell them is patience. The knowledge is there, now the patience, and to recognize once you've actually generated it, right? I think that's the best thing. It's more, the knowledge is there, the setup is there, we can recreate it. Now it's the patience and the little manipulation, the little technique. I always say graduate students are just over-educated technicians, right? So until you get that nice little probe to get the information you need from us. Yeah.
Thank you.
Thank you.
All right, so as Dr. Sills said, thank you everyone for attending.